Hello and welcome to today's video. In this video, we will solve the exercises 3, 4, 5 and 6 from the chapter 3 of the book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. Okay, the question 3 is let Q and Q star be as in exercise 2 means Q is set of all rational numbers and that is group under addition, and Q star is set of all non-zero rational number and that is group under multiplication. Okay, and we have to find the order of each element in Q and Q star. So we start with the solution. 0 belongs to Q, which is group under addition, is identity element, and we know that the order of identity element is always 1. So the order of 0 is 1. Okay. Let A belongs to Q such that A is a non-zero element. Now, in order to find the order of this element A, we have to find the we have to find a least positive integer n such that n trace n into A should be 0. So any such n does not exist because it is not possible in Q that we add some non-zero element to get 0. So all it is convention that if we cannot find such integer, then the order of that element is infinite. So all elements non-zero of Q, which is group under addition, has infinite order. Okay. Now for the set of non-zero rational number, which is group under multiplication, we will find the order of every element. So Q star is group under multiplication, and we know that 1, which belongs to Q star, is identity element, and we know that the order of identity element is 1. Similarly, -1 belongs to Q star, and if we take -1 to raise power 2, we will get identity. This means -1 has order 2. Okay. Let A belongs to Q star and this A is not equal to plus minus 1. Now we have to find the order of this element A, which is not equal to plus minus 1. We have to find least positive integer n such that A to raise power n should be equal to identity element. But there does not exist any such n, so the order of A is infinity. So every element of Q star other than plus minus 1 has infinite order. Okay, we move to the question number 4. For every group element A, we have to show that the order of A is equal to the order of inverse of A. Means an element and its inverse has the same order. Okay, we consider that the order of A is n and the order of A minus 1 or the order of inverse of A is m. We have to show we have to show that n is equal to m. Okay. Now since the order of A is n, this means A to raised power n is identity, and the order of A inverse is m. This means A inverse to raised power m is identity. Okay. Now consider A inverse to raised power n. That can be written as A to raised power minus n, and that can be written as A n to raised power minus 1. And we know that A n is identity, so it will be identity inverse, which is identity. Now we see that A inverse give identity when we take its power n, and the order of A inverse is m. And we know the definition of order, which is least positive integer. So it is clear that whenever an element give identity on some integer, it means that integer will be greater or equal to its order. So this n is clearly greater than m because m is least positive integer which A inverse gives identity, and A inverse is also giving the identity on power n, so n will be greater than m. Okay, also now consider A to raise power m can be written as A to raise power minus 1 to raise power minus 1 to raise power m, and that can be written as A to raise power minus 1 to raise power m and to raise power minus 1. And we know that A to raise power minus 1 to raise power m is identity, so this will be identity inverse, and that will be identity. And we see that am is identity, but the order of A is n, so n is the least such integer. This means this m will be greater than n, and now using these two inequalities we get the equality, that is n is equal to m, and that is what we want to prove. Okay, the next question is question 5. Let A belongs to a group and the order of A is equal to m. If n is relatively prime to m, show that A can be written as the nth power of some elements in group. Okay, since the order of A is equal to m and the GCD of n, m and m is equal to 1. We know that. It is given in the statement. We have to find x belongs to G such that A is equal to xn. Okay, means we have to find an element so that a can be written in the nth power of that element. It means we have to find the x. Okay, from the number theory, we know that if GCD of two integers is one, positive integer is 1, then there exist integers r and s such that Rn plus Sm is equal to 1. Now consider x is equal to a to raise power r. And if we take the power n on both sides, that will be ar to raise power n, and that will be a to raise power rn. Okay, instead of this r, I should write r to make the notations consistent. This r, this r, and this r. And from this equation, we know that Rn is 1 minus Sm. So this Rn can be written as a to raise power 1 minus Sm, and that can be written as a to raise power 1, a to raise power minus Sm. And that is a to raise power m to raise power minus s. And we know that a has order m, so am will be identity. So it will be a e to raise power minus s, and that will be a e, and this is a. So in this way we have find an element x so that a can be written as xn. Okay, we move to the next question. The question 6. Okay, in this question, the statement is give an example of a group G under addition that has a non-empty subset H that is closed but not a subgroup of G. And similarly, we have to give the same example for the group under multiplication. Okay, we know that we consider G to be set of integer, and we know that set of integer is group under addition. And we consider a subset H of G, which is all natural number. We can clearly see that whenever we will add two natural number, we will get again a natural number. H is closed under addition, but it is not a group because the identity does not belongs to H, or the additive inverse of any element does not belongs to H. So it is not a subgroup. Okay. And the other example is we consider G to be the set of all non-zero rational number, and we know that this is group under multiplication, and we consider a subset H which is plus minus 1, plus minus 2, 0, 0 is also there, and plus minus 3, and so on. This is of course closed under multiplication. H is closed under multiplication because whenever we will multiply two integers, we will get again the integer. But it is not a subgroup. H is not a subgroup because, for example, 3 belongs to H, and the multiplicative inverse of 3 is 1 by 3, and 1 by 3 does not belongs to H. So that's all about today's lecture. If it is helpful, then please subscribe the channel and like the video.